Welcome to Tutorial 9, where we're going to be learning about dummy variables and logistic regression. This tutorial is a combination of Chapter 9 and Chapter 10 in the Stata Companion to Political Analysis. We're going to learn about performing dummy variable regressions and about performing logistic regressions. Let us start with the regressions using dummy variables. A dummy variable can take on only two values, 1 and 0. Each case being analyzed either has the characteristic being measured, a code of 1, or doesn't have it, a code of 0. So a gender variable can be a dummy with females being coded 1 and males being coded 0, or vice versa. Let us open NES 2008. Also in this tutorial, we will be using do files. So let us open tutorial 9 do file and start running our commands. What we want to do here is to use the gender as an independent variable. When conducting regression using a dummy variable, you will always need to include the xi prefix. So we run our first command, which is xi colon regress Obama therm I dot the independent variable, which is gender here, and we include the weight. What the I is telling Stata is to create a set of dummy variables from the independent variable. So by default, the lowest coded value of the independent variable is treated as the omitted category and assigned a value of 0 on the dummy. So in our case, as males have the lower numeric code on gender, the xi prefix will create a dummy variable that is coded males 0, females 1. So let us consider the output. We can see that Stata has created a dummy variable, and we can see that women are coded 1 because of the numeric suffix _2 tells us that the cases coded 2 on the original variable gender are coded 1 on the new dummy. So Stata plugged the dummy into the analysis and arrived at estimates for the constant and the regression coefficient. We can see here our equation, and what this tells us is that the Obama feeling thermometer equals 56.27 plus 2.89 times the gender. What this means is that when the dummy switches from 0 to 1, the Obama ratings goes up on average 2.9 degrees. So females rated him at about 59 degrees, and males rated him at about 56 degrees. So we stop now and ask ourselves a question: was this gender difference produced by random sampling error? Well, no, according to the p-value, which equals 0.015. But do these differences account for a big amount of the variation in the Obama ratings? Not really. If we look at the adjusted r-squared, gender alone accounts for about 0.2% of the variation in the dependent variable. So clearly there are other variables that are driving this variation. Perhaps we can consider the partisanship variable, which we would expect to have a big effect on the Obama thermometer scale. The party ID 3 variable, we can see it by running the command for tab party ID, codes Democrats as 1, Independents as 2, and Republicans as 3. It's a categorical variable. Therefore, to use it in the regression, we must create a dummy variable for it. The rule for creating a dummy variable is that if the variable you want to dummyize has k categories, then you will need k minus 1 dummies to measure the variable. In this example, we want the omitted variable to be the independents and not the Democrats, since it would be the one that Stata would automatically omit if we don't specify anything. So what we can do around this default is to use the command char, which stands for characteristics. We type in char the variable name party ID 3, followed by, between square brackets, omit, and then the number of the numeric code of the category we want Stata to treat as omitted, and in this case it's 2. So we have the command here, and we run it. Stata will silently make the requested change. Now we turn to our regression. We run the command in our do file, so xi regress Obama therm, i.gender, i.party ID, and we have our weights. And from the output in front of us, we can extract a regression equation. First, let us get oriented by using the constant 58.185 as a point of reference. Remember that this value estimates the dependent variable when all the independent variables are 0. So 58.185 is the mean Obama rating for males who are independents. The regression coefficient on females tells us how much to adjust the male part of the intercept, controlling for partisanship. The partisanship dummies tell us how much to adjust the independent part of the intercept, controlling for gender. Thus, compared with independents, Democrats average 16 degrees higher and Republicans score 25 degrees lower. Let's go back to the output. Take a look at the p-values. The results show us that the Democrats are significantly different from independents, and that also Republicans are significantly different from independents on the Obama thermometer. The gender effect, however, is a weak one, and after taking party differences into account, the gender difference fades to insignificance. So overall, the model performs fairly well. The adjusted R-square of 0.3113 tells us that all the independent variables, taken together, account for 31% of the variation in the independent variable. After this brief introduction to using dummy variables in regressions, we now turn to the topic of logistic regression, which is designed to analyze the relationship between independent variables and a binary dependent variable. A binary variable, as its name suggests, can assume two values. Logistic regression, which is sometimes called the logistic model or logit model, is used for prediction of the probability of occurrence of an event by fitting data to a logit function logistic curve. It is another approach to prediction where you are predicting a binary outcome, which can assume only two values. There are two Stata commands which perform a binary logistic regression: the logit command and the logistic command. The logit command provides estimates for the coefficients in the logistic regression model, and the logistic command runs the same analysis as the logit command. However, it will express the coefficients as odds ratios. Another way to model binary outcome is with probit models. A probit model is a popular specification for an ordinal or a binary response model that employs a probit link function. This model is often estimated using a standard maximum likelihood procedure. You can run a probit model using the probit command in Stata. The probit model has been around longer than the logit model. They look identical, except that the logistic distribution tends to be a little flat-tailed. One of the reasons the logit model was formulated was that the probit model was difficult to compute because it involved calculating difficult integrals. Modern computing, however, has made this computation fairly simple. The coefficients obtained from the logit and probit models are also fairly close. However, the odds ratio makes the logit model easier to interpret. For this tutorial, we are going to be focusing on logistic regression models.
Let us now open the GSS 2006 dataset. We want to see what is the impact of education on whether a person voted or not. We want to run two commands: logit voted 04 educ and logistic voted 04. First, let us look at the output from the logit command. The logged odds of the voted for variable equals negative 2.215 plus 0.248 edu. What does this mean? Well, the constant is saying for us that people with no education, their estimated logged odds of voting is equal to negative 2.215. The logistic regression coefficient in education says that the logged odds of voting increases by 0.248 for each 1 year increase in education. So, as the independent variable increases, the likelihood of voting increases as well. But we want to know or ask ourselves if education has a statistically significant effect on the likelihood of voting. If you remember, in an OLS regression, Stata determines statistical significance by calculating a t-statistic and a p-value. In logistic regressions, however, Stata calculates a z-statistics and reports a two-tailed p-value. Interpretation of this p-value, which we see here displayed in the column labeled p greater than z, is directly analogous to ordinary regression. If the p-value is greater than 0.05, do not reject the null hypothesis. You conclude that the independent variable does not have a significant effect on the dependent variable. If the p-value is less than or equal to 0.05, on the other hand, then reject the null hypothesis, and we infer that the independent variable has a significant relationship with the dependent variable. So we go back to our output, we look at the p-value for the educ variable, and it's 0.000, so we can then conclude that, yes, indeed, education has a significant effect on voting turnout. Now let us look at the output of the logistic command. You see here that Stata has made the educ's regression coefficient in a different format. You see the entry here next to the educ in the column labeled odds ratio. Stata reports a value rounding up to 1.28 for the independent variable educ. The value of the odds ratio is often used to obtain a different estimate, which is the percentage change in the odds for each unit change in the independent variable. We can do a simple arithmetic here where we subtract 1 from the odds ratio and then multiply by 100. In our current example, 1.28 minus 1 times 100 equals 28. So we can say that for each year increment in education, it increases the odds of voting by 28%. And obviously this relationship is positive. That is, when the logistic regression coefficient is greater than 0, and the odds ratio is greater than 1. But communicating a negative relationship between the independent variable and the probability of the dependent variable, we look at the percentage change in the odds. We calculate it the same way. So suppose that we have an odds ratio of 0.28. We say 0.28 minus 1 times 100, and it gives us a negative 72. What this indicates is that a 1 unit change in the independent variable would decrease the odds of the dependent variable by 72%, and thus this is a negative relationship. Now, how strong is the relationship between years of education and the likelihood of voting? This is where the iteration lines of the logit results become especially important. If you want to know how well a model performs, you can compare the initial log likelihood with the final log likelihood. So if using education to predict voting worked about as well as not using education to predict voting, then the final log likelihood would be about the same as the initial log likelihood. If by contrast education improved the model's predictive power, then the two log likelihoods would be very different. To learn more about our model, we can look at the LR chi-square likelihood ratio and the pseudo R-square. Both these statistics are based on the difference between the initial log likelihood and the final log likelihood. Keep in mind that the interpretation of the pseudo R-square is not the same as in the OLS regression. What it is measuring is the strength of association between the dependent and independent variables. And Stata here is reporting a measure suggested by Daniel McFadden, and you can find more about that in the book, Stata Companion. So with this we can conclude that education is related to voting. However, it provides a less than complete explanation of it. Let us now try another example, but this time with multiple independent variables. We want to see if education affects voting behavior taking age into consideration. So we add age to our model. We run now two commands. Logistic voted 04 educ age, coif, and logistic voted 04 educ age. The output gives us the coefficient estimates that we can put into our model, and the logged odds of voting would equal negative 4.555 plus 0.298 educ plus 0.036 age. Again, understanding these coefficients, we follow a straightforward multiple regression protocol. The coefficient on educ 0.298 is telling us that controlling for age, each additional year of education increases the logged odds of voting by 0.298. Notice, however, that controlling for education, age is positively related to the likelihood of voting. So each 1 year increment in age produces an increase of 0.036 in the logged odds of voting. According to the Z statistic here, and the accompanying p-values, each independent variable is significantly related to the dependent variable. A small point here is that using the logistic and coif command is the same as using the logit command. However, with the logistic coif, you do not get the lines of iterations that you would in a logit command. However, the results are identical. Now, let us look at the odds ratios, which we can see here in the odds ratio column of the second set of results. So we see that after controlling for age, the effect of education is stronger than its uncontrolled effect, which we looked at earlier. So taking respondents' age differences into account, each additional year of schooling increases the odds ratio by 1.347 and boosts the odds of voting by about 35%. Remember, we get the 35% from subtracting 1 from 1.374 and multiplying by 10, which gives us a 34.7, round up to 35%. Also looking at the odds ratio for age at 1.037, which is greater than 1, we can see that there's a positive relationship between age and the likelihood of voting. So if we want to compare the two individuals having the same number of years of education, but they are different in 1 year of age, we can say that the older person would be 1.037 times more likely to vote than a younger person, thus translating into a 3.7% change in the odds. So each additional year in age increases the odds of voting by 4%. Okay, and then we want to know, how does our model perform? So we look at the pseudo R-square of 0.134. So we see that adding age to the model has increased the explanatory power, at least if we compare it with the simple analysis using education, which was our only predictor. And if you remember, this gave us a pseudo R-square of 0.083. Then we look at the likelihood ratio at 636.70. Then this defeats the null hypothesis as a p-value equals 0. And it tells us that compared to the know-nothing model, both the independent variables significantly improved the ability to predict the likelihood of voting. And finally, we look at the final iteration log likelihood for the voted 04 education age model at negative 2050.7253. And we can say that this is an improvement over the simpler voted 04 education model, which converged at a final iteration log likelihood of negative 2180.2633. So clearly, both models outperform the know-nothing model, in which neither independent variable is used to predict the likelihood of voting. The last thing we're going to learn in this tutorial is how to determine if knowing the independent variables are indeed offering us significant predictive leverage if we are comparing it with not knowing the independent variable. So suppose we want to compare the models that we just looked at, the full voted O4 educ age model with the so-called reduced voted O4 educ model. So we can see in our do files 4 lines of command. The first one is logistic voted O4 educ, and this is the logistic command that we've already seen and our reduced model. And then the estimates store educ underscore model is the command that is telling us to store the model's estimates using the estimates command. And then we have another logistic command, but for our fuller model, logistic voted O4 educ age. And then we have LR test. LR stands for likelihood ratio. So LR test educ underscore model comma force. And basically what this is saying is that telling Stata to compare the full model's likelihood ratio with the reduced model's likelihood ratio. So we look at the results. Stata reports a likelihood ratio of 259.08. Stata arrived at this number by starting with the log likelihood of the reduced model, subtracting the log likelihood of the full model, and then multiplying the result by -2. And just like any log likelihood ratio, this number is the chi-square test statistic. And the degrees of freedom here, they're equal to the number of predictors in the full model, 2, minus the number of predictors in the reduced model, so 1. And the p-value of 0 can make us conclude that compared with using education alone, adding age as an independent variable significantly improves the predictive power of our model.
This brings us to the end of this tutorial. You can still refer to chapters 9 and 10 in the Stata Companion book and learn about more commands such as the test command, the predict command, the adjust command, as well as the tabstat command.